Okay, so in this video we're going to look at this method which is called equating real and imaginary parts. And it's a method that's used to solve equations that have complex numbers in them. So let's look at an example when you definitely need to use this kind of method. This method's best used when you've got unknowns. Here we've got A and B, and the unknowns are real. Okay, so we're trying to find the value of A and B. And the method basically works by saying, well, if we know that the left-hand side is equal to the right-hand side, then these two complex numbers must be the same. For two complex numbers to be the same, the real parts must be the same. So here the real part is 7 on the left-hand side, and the real part on the right-hand side is 2a. They're basically the terms without I in it. So we know that 2a must be equal to 7. So we know that a is equal to 7 over 2. Similarly, we know that the imaginary parts must be the same as each other on the left and the right hand side. So the imaginary part on the left hand side, remember the imaginary part is the coefficient of I, so that's 6 on the left hand side, must be equal to the imaginary part on the right hand side, which is the coefficient of I, which is b. So we know that 6 must be equal to b, or b equals 6. So that's an example where you definitely kind of have to use comparing real and imaginary parts on the left and the right hand side. An example of where you could use it but it's easier not to is an example where you've got a complex number z and you're basically trying to work out what this complex number z is. So a lot of people jump straight away to using comparing real and imaginary parts. I'll show you how you would do that using real and imaginary parts by comparing real and imaginary parts. So what this method would involve is saying, well, we're told that z is a complex number. Obviously, it needs to be a complex number. So let's just say that let z equal a plus bi. And we're going to try and find out what a and b are. So this would be method 1. So we basically know that 3i multiplied by z, which we're calling a plus bi, the complex number a plus bi, must be equal to 7 plus 2i. And then expand the left-hand side, so we know that 3ai plus 3bi squared is equal to 7 plus 2i. And then, so we know that 3ai, I squared is minus 1, so actually we can simplify this to minus 3b. We never want to work with an equation which has I squared in, because we know I squared is real and it's equal to minus 1. And that must be equal to the right-hand side, which is 7 plus 2i. So if I make this left-hand side look a little bit more like a complex number, so the real part is minus 3b, and then plus the imaginary part, which is 3a times by I. So now I've written it like that. Hopefully it's quite clear to see that now I can equate the real parts. The real part on the left-hand side is minus 3b, and the real part on the right-hand side is 7. So minus 3b is equal to 7, so b equals minus 7 over 3. And similarly, if we look at the the imaginary parts, the coefficient of I on the left-hand side is 3a, and the coefficient of I on the right-hand side is 2, so I know that 3a is equal to 2, so a equals 2 over 3. So that's one way which is really common for people finding a complex number z. A better method for solving an equation like this would be just to rearrange it to get z on its own. If you divide both sides by 3i, you'd get 7 equals 7 plus 2i divided by 3i. And then you can basically simplify what z is. To divide two complex numbers, you times the top and the bottom of the fraction by the complex conjugate of the denominator. The complex conjugate of the denominator is minus 3i. Just change the sign of the imaginary part. If you prefer, you could think about that as 0 plus 3i. So the complex conjugate is 0 minus 3i. Change the sign of the imaginary part. So if we times the top by minus 3i and times the bottom by minus 3i, then straight away we're going to find out what z is. So on the top we'd have minus 21i, and then we'd have minus 6i squared all over minus 9i squared, So to get z equals minus 21i, I squared is minus 1, so we've got plus 6 over I squared is minus 1 times minus 9 is 9. So we could write that in this form. 6 over 9 is the real part. I'm just going to split this up into two fractions, and then minus 21 over 9i, and obviously you can simplify that to what we had before, which is 2 over 3 minus 7 over 3i, which is what we had before. So hopefully you can see that this method on the right is slightly easier. So let's have a look at a couple of examples then. So here we've got an equation, and we have these constants a and b that we need to find, and we're told that a and b are real, and that's important, and we'll know why that's important in a second. So we're going to use the method of equating real and imaginary parts, or another way of saying that is comparing real and imaginary parts. So we've got this complex number 3 plus 5i on the left hand side, and we've got another complex number on the right hand side. Let's expand the brackets so that we can find out what the real part and what the imaginary part is. So if we expand this bracket, we're going to have a plus ai plus bi and plus bi squared. So we're going to have 3 plus 5i, and then we don't like I squared in an equation because I squared is just minus 1. I squared is a real number. So actually we're going to have a plus ai plus bi, and I squared is minus 1, so b times minus 1 is minus b. So in order to compare real and imaginary parts, we're going to have to make it really clear on the right hand side what's the real part of this complex number and what's the imaginary part. So let's collect together the real parts. So the parts without iron are a and minus b. So we've got a minus b is the real part of the complex number on the right hand side. And actually you can put a bracket around it if you want to make it really clear that that's the real part. And then we're going to take I outside of a bracket to find out what the imaginary part is. So the imaginary part is a plus b. So let's compare real parts then. So we know that 3 must be the same as a minus b. That's the real part of these complex numbers. So that tells us that 3 is equal to a minus b. And we could also get another equation by looking at the imaginary parts and saying they must be equal. So we've got plus 5 is the imaginary part on the left hand side, and a plus b is the imaginary part on the right hand side. So we know that 5 must be equal to a plus b. And then we can just solve these simultaneously to find out the values of a and b. So because I've got minus b here and plus b here on this equation, I'm going to add the two equations together. So we'd get 8 equals 2a, so a equals 4. To find the value of b, I'm just going to use equation 2. So a plus 4 plus 1 equals 5, so b equals 1. The part where we've used the fact that a and b are real is this part here, because we've said that the real part of this complex number is a minus b. So in order for us to be certain that this is real, then we need to make sure that a and b are real numbers.